learning basics. So you will find all the slides and all the exercise tasks online. So if you go to nabacam.org/teaching, yeah, machine learning and quantum alchemy, that's what we're doing. So if you check this material, there's everything there. The tasks will stay there even after the course. So don't worry, didn't manage to download something on time. All right, so what do we want to do in the next half hour? So I want to tell a little bit about what's the fundamental promise of machine learning. So what can you do with it, and what can you expect it to do, what can you not expect it to do? We'll talk about what are the key ingredients, and we will look at two big problem classes to start with. And after that, we will look into two algorithms just to get this started, and they're deliberately chosen to be maybe not the most sophisticated ones, but they're chosen to be something that you can implement in right after this with own data. So as I said, all the material content is online, will stay there. And for Python, if you have a working Python environment on your computer and you'd like to use that, feel free to do that. If you don't, I suggest that you use the free version of Google Colab, which is basically Python in the browser, no need to install anything, and that should work for everybody with a Google account. I will use that just so it looks the same for everybody else, but feel free to use whatever you like. All right, let's get started. So machine learning, in the way we think about it in chemistry and physics, is we're trying to find a surrogate model, something which is cheaper, which is faster, but gives us the same answer. And so it's really a statistical modeling technique. So it's not like quantum chemistry, where you have a predictor with a physical model and you try to predict what's happening from that. It's a statistical model. And machine learning has one fundamental promise. There's even a mathematical guarantee for that in our specific case. And it's the promise that if you have more data, then your model will get strictly better. Or in other words, by adding more data, it cannot get worse. That's a very funny promise. Because it means you have a guaranteed way how you can make your models more accurate. That's something that, for example, in computational chemistry or physics, we usually don't have. Now, it's also nice in a sense that all you have to do to make your model better is to generate more data points that you can put into the training data set. Right? If you know more real answers, then that's sufficient to improve the model. It also helps to choose a better model architecture, better model kind. And that's what you will learn today, and tomorrow you will get to know a little familiar different families of model classes and where they work and where they don't. But the one thing that it is not is a black box. So if you say, I want to model my problem and I want to make it easier, and I just have a bunch of training data and I throw it at the machine, that doesn't mean that this machine learning model is actually going to be helpful. So you still have to know what is in your data, how to represent it, and which model family to choose for the problem that you look at. And that takes a little bit of fiddling around and experimenting. So building a good machine learning model consists of a long series of try and error. So you have an idea, you have an hypothesis, you think of something, and you build a new model. So in principle, it's a mapping. It takes a bunch of input and it produces one value. Say we have a molecule and we want to know what is this molecule's energy. Is it stable or not? Right? That's a property, it's a scalar property. So in machine learning, we have specific names for that. You will need the names because all libraries and all documentation and all papers will use those names. So you know mathematical functions, right? F of x is something. Now it's use that as an analogy. F is the property, right? The function name, what we have is the actual property that we care about. And x describes whatever we use as input, and that would be our features. So when people talk about feature space, what they mean is whatever you put there. And different name for the same thing, especially for kernel methods, would be representation. Means the same thing. And then this functional expression that you know, that would be the model. And that is usually a mathematical expression. Now, what we do is we build a model. We come up with something data-driven, so we need to talk about what data is called. And there's a bunch of training data, which means points where you know what the function value should be. Right? So, you know, I want my model, and I want to make sure that the model, if evaluated at that point, gives me that value. And if evaluated at that point, gives me this value. And all those points, those are the training data points. Now, there's the training points, which is the position where you happen to know the value of the function. And then there is the so-called labels, which are the corresponding values. If you, for example, say, I want to build a model that predicts toxicity of a molecule, right? Is it dangerous for me? And that could also be a label, right? Yes or no categorical labels are fine as well. And we will look at both classification, where you predict a group, and regression, where you predict a value. Is that clear with the names? Very good. All right, now in quantum chemistry, there's an analogy. Right? So you have a molecule, and you can take this molecule, and physically speaking, we would now come up with a Hamiltonian, right? To describe it, to calculate the property. What does the Hamiltonian depend on? Well, a bunch of input, right? So nuclear positions, nuclear charges, number of electrons, and spin. And what does it give us? By virtue of Schrödinger's equation, it gives us a wave function, which we can then query to get some scalar properties. So you would, in this comparison, call all of these features, right? Because those are the arguments of the function that you're trying to learn. And the Hamiltonian becomes the model. So conceptually, again, it's a direct mapping that you have, and that's exactly what you would learn for different properties. So what we need to do is we need to find a way to get a molecule to be part of a machine learning representation. And I need a mathematical object. I need to take the physical system and convert it into something that has a mathematical structure. It can be a vector, it can be a matrix, right? It can be anything. It needs to be a mathematical object. I can't just say caffeine, I need something else. Now, it's a tricky business to come up with a good representation. Why can't I just take this? I mean, it's complete, right? It has all the ingredients. We know from quantum chemistry this works, right? Positions, nuclei, everything's there. Any idea why that might not be brilliant? So, for example, there are different physical properties that reality adheres to. Molecule over here is the same as the molecule over here, same as the molecule over here. Translational symmetry is a thing. Right? Rotational symmetry is a thing. But the coordinates, the actual spatial coordinates, they change. If I move my molecule through the room, then these things change. So how do I train this to the system? Well, with more data. I would need to pay data just to learn translational symmetry, which is not very fascinating. So what you would do is you would come up with a representation that, for example, already knows about translational symmetry, which means it's reasonably complicated to come up with something that is competitive. It's a challenge. We will look at a few examples of this. But you then can apply this to different problem classes. So now you have your chemical, your physical system represented by whatever mathematical object. And you have your property that you want to learn, and you have your bunch of points where you know that for this molecule, the property is that, for the other molecule, the property is this. Now, there's different ways how you can go about it. And typically, you group this into supervised learning, means you have labels, and unsupervised learning, meaning you don't have the labels. For example, if you want to learn, is my molecule dangerous for me or not? Right? Is it toxic? That's a classification problem. You have two groups, yes and no. Try to tell them apart. If you want to know what is the absorption spectra of my molecule, that's a regression problem, right? The answer is a number or some discretized prediction. That's a regression problem. Now, in both cases, in your training data, you need to know that, right? Now, you could, for example, also ask the question, I happen to have a long list of molecules that people have synthesized. What do they have in common, right? Are there any groups of things? That would be clustering. So you say, I don't know how many clusters there are. I don't have the labels. Nobody's produced the labels, but I would like to group them, please. So give me 5 groups, give me 7 groups, something like that. For completeness, there's also the regression equivalent for unsupervised learning, but that's rarely used in chemistry. So we'll not look at association very much. So let's have a look at the supervised learning part, because that's, I think, more intuitive to start. So in classification, the purpose is to tell two things apart, or many things apart. A classical example that you will see if you look at machine learning online is digits, reading handwriting. Because we know there's 10 digits. So basically what you're doing is you're classifying, right? Somebody wrote something on an envelope, which postal code did they need? And that's a reasonably well-defined problem. It's hard to get it right from a balance perspective. So imagine I have a system which has or a database which contains molecules that are potentially dangerous, and let's say 5 of them are dangerous, and 95 of them are harmless. I can propose a very bad model that has a very good score. And the answer is it's always not dangerous, right? It's correct in 95% of the cases. There's a stupid model, but it's very accurate. So the moment you have some kind of imbalance in the data set, it's hard to make sure that you really choose the right model. So classification, there's usually two main families to keep in mind of. It's either you want to say, is my handwriting digit, is this a 0 or anything else? There would be a 1 versus all classifier. Or you say, is it a 0 or is it a 1? You want to tell two groups apart. There's a 1 versus 1 classifier. So in both flavors are perfectly fine, right? You will never find a book, a paper, online tutorial that tells you this is how you do machine learning. Depends on your data set, it's trial and error, so there's no general wisdom that this model is strictly better than any other. But they are different strategies that maybe sometimes this works better, maybe sometimes the other works better. And there are common algorithms for this, and we will look at the two most illustrative ones of those, which are decision trees and k-nearest neighbors. You can also use neural networks for that, but it's usually overkill. And the other class is regression. So what's hard in regression? It's very sensitive to individual errors. If your training data, for example, is measured experimentally, then every experiment has some kind of uncertainty, has some kind of noise, accuracy level, and that is going to hurt the data. It's going to hurt the model. And in fact, this relates to something that people use actively to make sure that, for example, you can't just download the contents of the web page and build a large language model. You can poison data sets by exactly this, right? Produce data points which are designed to hurt models, right? This is actively exploited. But the main point is, if you have noisy data, that requires a different treatment than if you have almost noise-free data. In regression, that's a big problem. It's usually solved with regularization. We will talk about that tomorrow. Now, common strategies for that are kernel methods. So that's a specific group of techniques. We will look at the more formal picture of that tomorrow. But the main representatives that you might know are support vector machines or Gaussian process regression. We will look at something which sits right in between of the two. We will look at kernel-ridge regression tomorrow, because that's something that you can implement in a few lines of Python. Now, what is regression also very good at is neural networks. They usually allow you to circumvent the representation problem. So this thing. Right? Neural networks are very good at implicitly generating this mathematical structure. Otherwise, for kernel methods, you have to handcraft it. All right. Is it clear up to here? Supervised, unsupervised learning, classification, regression. Are we happy? Very good. If not, please interrupt me, right? Okay, let's have a look at the first algorithm, decision trees. Decision trees are very intuitive. Right? So the idea is you have a big table, right? You have different properties of a given molecule. And now, depending on those different properties, you decide whether, for example, it's dangerous or not dangerous. So let's have a look at this. Let's say we have two features. One could be, say, the homo-lumo gap. Look, the other one, that could be the weight. Right? Just simple stuff. Now we have a bunch of data points. And I don't know whether we can turn off these lights. Is that possible to only turn off these lights? Only these lights here in front, but not the others. That's a bit much. Let's turn them on, and I'll just make it bigger. All right, so maybe now it's easier to see. We have a bunch of points. These ones over here, they are orange, so they are one class. Let's say they are dangerous. Now we have the blue points over here, which are not dangerous. So how can we tell them apart? A decision tree will come up with criteria. You say you first divide all the points based on whether this one feature that you have is larger or smaller than some threshold. If it's larger, you say it's blue, so not dangerous. And then you choose one group and you subdivide again. You choose that group and you say, only for that part, not for this one, right? Only for that part over here, we subdivide again if feature 2 is larger or smaller than some threshold. This way you have isolated these points over here and separated them from the blue points over there. So what does that mean in terms of tree? The first question is this feature 1 larger than A? If yes, the answer is blue. If not, we ask the question, is feature 2 larger than B? If yes, the answer is orange. Otherwise, the answer is blue. And because it's a hierarchical structure, that's what you call a decision tree. So every node that you have asks a question. It chooses a feature, and it has a threshold. Then you say, well, on the one side, on the other side, what happens? Does it make sense so far? What's the beauty of this? You can do this on the back of the envelope, right? You can explain this to your drunk friend. This is okay. It has one obvious, or maybe not as obvious, but it has one particular disadvantage. It's terribly sensitive to the position of those thresholds, right? So for example, here you see the separation between the orange point and the blue points is not that big. And the other part is it's sensitive to variable transforms. If I take my whole bunch of data points and I rotate a little bit, let's rotate left a little bit, right? So this is our new rotated plot. It's the same plot, just rotated by 50 degrees to the left. Now I can do this with one decision, which of course tells you that if you have a high-dimensional data set, decision trees depend very much on what exactly it is the feature that you have, right? If you rotate your data set or choose slightly different features, then whether you can classify it or not, or how complicated it is to classify, is a little bit finicky. Is that clear why? The other problem, which is not obvious at all, is the thing that every time you branch, you reduce the number of data points you have, right? Because you just made the decision, right? You took the whole data set, you divided this into parts, and now you're subdividing every part. Which means that imagine you halve your data set every time you do one more iteration, one more layer. You have 100 data points here. Now you have 50 data points here. I have 25 data points here. So this means if you want to have more decisions, you need exponentially more data. You need 2 to the n, where n is the level of your tree, more data points to be able to make any kind of informed decision at all. So decision trees work very well if you can live with a simple decision diagram and you have plenty of data. Then they're fun. So it's very easy to interpret, and it works very nicely if you have big amounts of data points. It's somewhat costly to train. I will not show you the about 5 slides that I need to explain how you actually train them. That's one of the reasons why we don't do this in our hands-on practice, because you can't easily implement it yourself. It's an entropy argument, how they're usually trained, and also it's not very convenient because they're prone to overfitting, right? So they're very specialized to the one data set that you have, because you have to put your threshold somewhere, and where you put it depends on your current data point. There's no mathematical argument where exactly you put this threshold, right? You can move it a little bit to the left and the right. There's a degree of freedom how to choose. Now, the one thing that we will do today, is very easy to implement in Python, but it's instructive, is nearest neighbor model. You can use that for classification and for regression. It's a very, very simple concept. So imagine we have our systems, and every point here that you see is a training data point. So what does the nearest neighbor model say? It says, when you want to know the value of a function or the label whether a molecule is dangerous or not, you just pick the one thing in your training data set which is the most similar, and you just say whatever you have in the data set for that one. So these are the training points, right? Again, blue, harmless, orange, dangerous. So if you ask for a molecule, which is here, then the closest one is that point, and the closest one happens to be dangerous, so you just postulate molecule dangerous. Very simple thing. You can do this with number values, where you say, I have my training data, and now when you ask me about some number value, I just give you the one that is closest, that I happen to know. But you can also do the classification. Here again, it's our classification in orange and blue. Is the idea clear of nearest neighbors? Okay. So what you see here is the map, right? You have a 2D feature space and you see those individual cells. This is the area which is closest to the corresponding point that is in here. Called a Voronoi tessellation, used in computer graphics as well, but nonetheless, these are the boxes. And there's one thing that's important to know, with this red line. That's the line where the model switches from answer blue to answer orange. And this line is called the decision boundary. And it's very specific to the particular model that you built. To an extent that people use that to prove that somebody stole their model. Because if I know my model, right, I can ask for that data point, the answer should be blue. And ask for this data point, the answer should be orange. If I do this in very many places, I can prove that your model has the same decision boundary as mine, which is nigh impossible unless you stole it. So it's used for fingerprinting. But nonetheless, this is the surface where the answer switches. Is that clear? All right. Now, there's a generalization to this, because sometimes maybe just asking for the nearest neighbor is a little bit under complex. So the generalization of that is the k nearest neighbors. The k nearest neighbors has a very simple concept. You do not only give the label of the closest point, you search for the k closest points, and then have a majority vote. I ask for the 5 closest points, and if of the 5 closest points, 3 happen to be blue, my answer is blue. If 3 happen to be orange, the answer is orange. Which also already tells you that something with an even k is not exactly fun, right? Because then how do you do majority votes? But for regression, you can do the very same thing. You can say, if I have the k nearest neighbors, I take the average of my k nearest values, and that's my answer. Now, there's one problem. If you make k too big, you become oblivious to your actual data. Look at this. This, what you see down here, is the decision boundary. So let's say k is 1, right? New data set. K is 1. There's a few orange points over here, right? That's why you have a decision boundary around that that says the answer here is blue, and in all those patches, the answer is orange. That's k is 1. Now you can see it's maybe not as great if k is 1, because what if these labels are wrong, right? So I'm not entirely sure whether I should trust the individual data point over here. This doesn't really give a coherent picture, right? Now you can make k bigger. You can say, what about the 5 nearest neighbors, right? And you see that those islands here, they go away, and then this area becomes bigger. That is supposed to be orange. And now you see that some of those orange points actually lie in blue territory, because all their neighbors are blue, so the answer is probably should have been blue. Maybe somebody didn't measure accurately, had a wrong molecule, whatever. Now you can make k bigger. Now look what's happening to the shape. Has less and less features, right? And ultimately, if we make this a very collaborative agreement of the 50 closest points, this is more or less featureless. So exactly what you have. So this means if you make your corresponding k too small, you become very sensitive to the exact individual value. If you make K terribly big, you lose all kind of resolution of what's going on. Does that make sense? That's a common thing in many machine learning algorithms. They have parameters that you can adjust, and they are called hyperparameters. K would be one of those. And the hyperparameter is something that you kind of have to roll. There are ways how to choose them in a very well-defined manner. It's called cross-validation. We'll do that later. But ultimately, they are free parameters. The same way as you choose which model to do, which model to build for that particular data set, you're also free to choose whatever hyperparameter value it should be. If, for example, you know that all those data points, right, they have been done by my friend, and he's never wrong, right? He's very careful, very meticulous, is a perfect measurement. I should trust those values. If the point is orange, the point is orange. Then K probably should be 1 in this particular plot. If this is some data that you found lying on the street and you don't really know whether it's trustworthy, then probably K should be bigger, right? So it depends on your data set, it depends on the data that you have, it depends on the kind of property you look at. That's why there is no unique answer which one of those is the way to go. All right, so K nearest neighbors is really, really simple. So if you need a cheap model, that's a good thing to do. It becomes hard if you have many features. So that's the main limitation of K nearest neighbors. If I have a long list of features that I use to calculate the similarity of molecules and systems, then that's a problem. Why is that? Because funnily enough, in high dimensions, you can roll 2 random points, and they will almost all of them will be far away from each other. It's actually quite hard to roll 2 random points in high dimensions that are close by. So that means that in higher dimensions, K nearest neighbor starts to lose meaning. Right? So if you have something like 5 to 10 features, that's probably going to work. Beyond that, accuracy is going to deteriorate. All right, so that should be enough theory for today. We will now look at how to do this in a practical manner. I just want to quickly summarize. So we're exploiting similarity, right? So any model needs to have some kind of way to tell you which points are similar, because that's where you would take the answer from. That's why K nearest neighbor is a very intuitive thing. It is not parameter free, right? In machine learning, one of the parameters that you choose is which model to take. That's already a selection. And yes, there is lots of empirical knowledge on statements along the lines of, if your data set looks like this, use that model. There's lots of this experiential value. But there's not a unique way to predict that. So get used to the fact that when you build your own models, you will find yourself trying out stuff quite a bit. And that's probably something like 90% of the work. So don't be surprised, we will do exactly this today. I have a bunch of tasks, but are there any further questions to all of this? Okay, very good. Then probably don't need to record the rest.
Why you like Guido? Select, for example, because they are proportional, or the proportion between them don't change. The distance is bigger.
So if you get the question right, you're asking why then in high dimensions are we just accepting the markers? Okay. The problem is that what is close becomes everything in line. Let me illustrate. I have just 2D, right? There's one point in here, and there's a circle. Everything on the circle is at the same distance from the cross center, but the points on the circle, they're close to each other. Now, let's take the same thing, and let's make this a sphere. Very, very bad at drawing 3D, right? So now you have a sphere. Every point on the sphere has exactly the same distance from the point in the center. But now the distance between two random points on the sphere is a little larger than the distance of two random points on the circle. So now you can generalize this. This is the number of dimensions. What is the expectation value of the distance between two random points? Looks like this. So the standard deviation looks like this, which means that the difference, so the variation in any pairwise distance within your training set becomes smaller and smaller. At some point, every point, the limit of infinite dimensions, every point is exactly as far away from any other training point that you have. And that's the problem, because then basically all points are your neighbors, which happen with all points. Have a question? Okay. And let's look at the tasks. Make this a little. Yeah. Yes, so you will find all the information online. There is a link to the code editor as well, so you don't have to copy it. If you want to use Python for your own installation, you will need the packages that are listed here. And if you find yourself wanting to recap a little bit on scientific Python, if there's something you're missing, there's a link here to your practicals that might be helpful. So, quick question. Who of you is programming regularly? Sometimes? Okay. Who has no programming experience at all? All right. Then that helps me. So I will briefly explain what the task is. I will go through the task with you once, and I will ask you to try them on your own, in your personal speed that you like to do the task. I will be available for questions. I will walk around and look over your shoulder. So if you have any problems, let me know. And the goal is that you play around with that. Right? Your goal should not be to write the perfect code. Right? The goal should be to try stuff out. And if you have any questions. All right, so today we will start with learning the Morse potential. It has a nice advantage of being a 1D problem, so you can easily look at it. So, Morse potential is a binding potential. Model is a chemical bond. And we will use that as a function to learn terms. So first, first you're asked to implement the Morse potential. So you'll find this on Wikipedia. It also has a much nicer code than my hand drawing. So you see the potential. The typical volume potential is an equation. You can assume all parameters to be 1. And first, we will look at it. So, first question is write a function that does that. During the task, we'll find these type inputs. So they are supposed to help you a little bit what the individual arguments are. So function force potential, which takes a single float argument, which is the distance, and it shall return the corresponding potential. All right. And then once you did that, was implemented that, and you plotted it, so you can look at it and see that the function E looks like the one that we're looking for, and then we have an idea of what to visualize points. Now we want to generate random data points like that, because that's going to be our training. We need the real answer to be able to get the point. Then we want to do the nearest data prediction. So that you write a function that takes all the training data points and for a given query returns the one which is closest. There are different strategies how you can implement that. We will discuss them together. And then at that point, we will talk about all of that together because the remaining part is going to be about cycle verb. I'll tell you about cycle verb first. Trying to do task number 4. If you have any questions, let me know. For those of you who have experience and feel bored, there is another section down here. That's what it's. But let's try to go up to 4 first. Does everybody have access to the Python installation? Be it Google Colab, be it something else? Anybody without Python access? No? Very good.
Report this, yeah. For the people that are seeing the provision.
Okay. So let's build this. Let's do the first function together. So we have the Morse potential, and we would like to write a function which does exactly one thing, namely take a distance and then return the corresponding value. So in our expression over here, x would be the distance, and that should be it. Let's do that together. Can you read that? Is that big enough? Okay, so I copied the definition, right? So we say we would like to calculate the Morse potential of a function. So we can say return 1 minus the exponential. I will load that in a second. Distance minus 1 squared. So the explanation would be we first load our numerical Python module, NumPy, which gives us convenience functions. If you have ever find yourself in the situation that you would like to build anything which is numerics heavy in Python, you probably want to use NumPy for this. One of the most efficient ways to do that. So now then we write a function which takes the name Morse potential. For those online, I highlight this. Which takes the name Morse potential and has one single argument, name distance, and of type float. And we already tell it's going to return just a float. And then the function uses the exponential from the package NumPy. So this means from the package NumPy, take the function exp. So now I can inquire Morse potential of 1. It takes a while because it has to load the virtual machine initially. Any subsequent call will be faster. So for 1, it's 0. For 2, it's positive. And for 0.5, also positive. So we know it's our exponential shape. Is that clear up until here? Okay. Then let's plot this together. So I will copy this because I gave the code to you. So now this is another package. Matplotlib is the standard package to do plotting or visualization in Python. It's modeled after MATLAB, but still fairly simple. So I brought you 2 examples here, the plot function and the scatter function. The main idea is if you plot this, you will get a line between the points, and if you scatter, you get exactly the points. I will share the code later on, right? So it will all be online, don't worry. Okay, so now we have our package. What we would like to do is we would like to plot what this function, Morse potential, looks like, depending on whatever distance you plug in. So for that, we need some points where we can evaluate the corresponding function. And that could be done with NumPy linspace. The name stands for linear spacing. There's also log space, which does exactly what you think it does. And we can define some start, say 0.1, and we can define some end, which is 10. And if I run it, this gives me 50 points from 0.1 to 10. Now I can get the corresponding y values, and that could be Morse potential for every value in there. And then I use what I gave you in the task. It's a little smaller. Now you can see both the code and the plot, right? So we have first, we got our 10 our data points over the domain, and then we evaluate the Morse potential for each of those, and now we plot this. Does it make sense so far? Okay. So let's talk about the region of interest. The task stipulated that you shall identify the domain of interest, which is the part that we want to learn. So why would we care? How do you identify the domain of interest? It's a region of the function where stuff is happening. So that would be for small values over here. You notice that the function value is basically constant for large distances. Since it's supposed to model a chemical bond, this is exactly what you would expect from a chemical bond. Right? So at large distances, already the atoms are separated. There should be no potential. Now, for our machine learning applications, that's a boring part, because there's no need to actually learn this. And if we do k nearest neighbors, if I have any point here on this flat line, then my k nearest neighbor model is perfect for larger distances, because what's the nearest point that I have? The largest data point in my data set, which happens to have the correct value. So I don't need training data that goes on and on the constant line. What I need to model is the place where the function actually changes. So the domain of interest, if you look at this, could be something like 5 or 6 maybe, right? So until it reaches the almost flat line. So I would argue maybe up until 6. But this is, you can choose whatever you want. Make it such that if you continue, make it such that you can choose up until where you run the data or generate the data, so you can play around with this later on. You can see what happens if you make the domain go from 0 to 100. Right? Remember about this this degenerate bad model that I mentioned earlier? Right? Something where we always say a molecule is not dangerous. That's exactly the case, right? Let me propose the Guido model. The answer is 1. That's pretty decent. It's also fairly useless, but it's decent. So that's why you need to choose the corresponding right value that you care about. You will see that in learning if you ever change this later. All right? Make sense? Very good. Then please continue from here on to task 4.
I want, if I select, for example, this number of resolution of points, I select point 1. There is not an imbalance in the recursive part. I will not will want to have
if you look on the web page, we have this open. We now have the code. You've seen this, and now we care about the random data points. So the task was write a function to generate n uniformly random data points. That's the reason why we had to come up with a domain first, the domain of interest, because we don't have a domain that we can't get uniformly distributed points. And then we want to have a data set where you can adjust the size of the data set, because that will be crucial to understand later on what's going on, how a model benefits from more data, right? So what we want, something which is adjustable, which returns our tuple of points. So we will get one thing, which is the positions at which the potential is evaluated. So in our plot, that could be this one, this one, and this one, right? So the positions, that will be the first entry. And now we need ys, which is the corresponding values, right? So that would be the corresponding function values that we get. Let's do that in code. Well, the task is do that. So we write def to define a function which says generate data set. So now we need the x values first. So that would be the distances. And you're totally free in how you name it. I like to use the convention. If it has an s at the end, it's a plural of something. If it doesn't have the s, it's a single value. So x is one position, xs is many positions. Don't have to do that. It just might be helpful if you work on larger code bases. So how do you generate something uniform? There's NumPy random uniform. If you want to look it up, the corresponding Python course that is mentioned a few times has far down also something about array generators, which also contain the random numbers. Okay, so we do np random uniform. And np random uniform takes 3 arguments. The first one is what's the lower end of your domain. Second one is what's the higher end of your domain, and then you can tell how many of those points you'd like to have. So we can say our lower end, say 0.1, our upper end is, in my plot, 6, and the size is n, because that's how many points we would like to have. That gives us n random points. Every time you run this function, you will get new random points. So now we need the y values, right? We know where we want to evaluate our function. Now we want to evaluate the function at every point. And you can use the same logic that we had before. So for example, this one here, right? That would be the list comprehension. Technical term for this, because I will share the code later on. The technical term for this is list comprehension, this bracket notation. Now the problem is that Python is not a fast language on its own. It's an interpreted language. It will be slow, but with NumPy you can make it much faster. The reason is that NumPy under the hood uses C or Fortran implementations of the corresponding functions. So especially if you have many data points, that's faster. If all you have is 3 data points, then don't bother, right? The conversion time to NumPy is gonna eat all your performance gain. But if you have 1,000 points, it makes a difference. So what you can do is you can use the fact that this function, Morse potential here, even though defined for a single scalar argument to return a single scalar value, in NumPy can be applied to a whole array at once. So if instead of a single value for distance, you put a full NumPy array, then the expression here will be to calculate the exponential of this argument where distance is an array. And then NumPy will do something which they call broadcasting, which means they apply the corresponding function that you have to each and every value. Which means you don't write the for loop yourself. The for loop runs in NumPy, which is numerically much more efficient because that's low level, right? That's C of Fortran. So that way we can write that ys shall be Morse potential of xs. Now, if you maybe come from a strongly typed language like C or Fortran, where you have specified arguments, you might say, wait, what? How is this supposed to work? I told Python this is a float. Why does it take an array? And the reason is Python is a so-called duck-typed language, or weakly typed language. Duck typing comes from this English expression that if it walks like a duck and if it quacks like a duck, it's probably a duck. So the reason is all you need to do is you need to pass an object that behaves as if it was a single value. It doesn't actually have to be a single value. So since NumPy knows how to deal with the fact that if it's interpreted as a single value, Python lets you do that. So these type hints that you have here, they are called type hints because they're more of a recommendation. And they help you. I put them there and on the online document and the task, so you can easily understand what should go in, what should go out. But they're by no means enforced. Python lets you do whatever you want. Is that clear? So that's one of the strengths of NumPy, that it lets you do that you can automatically change a mathematical operation from being applied to a single value, to a vector, to a matrix. This all does the same thing, just element-wise right now. Make sense? Very good. So now we were supposed to return the tuple, right? We were supposed to return both things. So the positions where we evaluated the function and the values that we got. So we do return xs, ys. To return one thing, just return xs. You will get just the return, this one return value. But if you separate them by commas, you can put more over here, right? So if you want to return more things, you will return a tuple. That's an easy way to make a function return independent things that kind of belong together. And here, xs and ys belong together because there's no way to analyze or to consider, to understand what ys holds unless you also know where the function has been evaluated. Otherwise, it makes no sense. Any questions up until here? Okay. So let's run it. generate data set 2. Right, I want to have 2 points. Gives me 2 points, 2 random points, and 2 corresponding y values. Now I can run it again. The first point was 2.4. So I run it again, and now the first point is 2.6. Right? So every time you ask for a new random number, new random vector, you get a new set of random numbers. Any questions? If you want to know more about different kinds of distributions of random numbers, in NumPy random, there's all sorts of distributions. Right? So you can have a Gaussian distribution, uniform, you can bias, whatever you want. So that would be a good place to start if you need more random numbers. Okay. So that was task 3. Because now we have a way to generate our data set. It's randomized, which is good because all of machine learning theory and proofs usually rely on randomized data sets. And now we want to build the nearest neighbor prediction. Who tried to write nearest neighbors by hand? Is that where everybody currently is? Trying to do the task 4? All right, then let's take a few more minutes to do task 4, maybe 10 more minutes, and then we look at that. I don't know what's customary here. Should we maybe take a short break? That's perfect, right? So we're the perfect host. So let's maybe take a brief refresher, 5 to 10 minutes, and then take it from there. All right. Let's take one step back and let's quickly discuss what exactly task 4 is about. So we will take still a few minutes so you can try to implement it, but let's think about how one could implement it. The task is to implement nearest neighbor prediction. So we have one set of training data, and the prediction that we return is the value of the function at the closest point towards the query. So in my diagram, if I have those 3 points, if I ask for this position over here, what I want to return is the label of the closest, right? That would be this one. If I ask about that position over here, I want to return the value of the closest point, which is that one. Right? Because this is the closest. So what you need to do is look at all the training data that you got. Right? That would be training XS and training YS. Right? Yeah?
A question that a student has is that way you showed it's usually KNN is usually for classification. They are not seeing a classification in that example.
You can do k-nearest neighbors for regression. I mean, that's exactly what we're doing. It's k-nearest neighbors is most used for classification. That's correct, but you can use it for regression. And I like in this introductory courses that we do algorithms that you can implement from scratch, everything, the full details, so you understand what's going on. And then, of course, later, feel free to choose to use scikit-learn and do everything the library way. That's encouraged, because, well, the library is usually better at solving the problems. But it's helpful that you did it once yourself to understand what's going on. And for that, we use this because that's easy to implement. So you will see the problem with regression and one nearest neighbors very quickly, and that's exactly one of the things that we look at in the later task. So for the prediction, what you have is the XS, those are the red bars over here, right? That would be the position at which the function has been evaluated. That would be training XS. You have the corresponding array of the Y values. That would be the red points, where you know the true answer. Now you query it at one place, namely position. You're supposed to figure out which point is closest in the vector training XS, figure out what's the nearest neighbor, the one nearest neighbor. Then you look up what's the corresponding function value that I have in training YS. That's what you return. So that's the rough idea. There's very many different ways how you can do it. Is the rough idea clear? All right, let's take another 10 minutes to try to implement that, and then we do it together. All right, so the task was we want to predict the nearest neighbor, and for that we need to find the one point which is closest in the training data. So let's try to stick to NumPy because that's the most efficient way of going about it. I copy this. So we say we create a new function which takes 3 arguments. The first one is the position. That's where we want to evaluate our model, the single point. Then we have the x values and the y values, so the positions at which we have evaluated our Morse potential, and the corresponding values of the Morse potential. So we need to find the closest point within this one. So what's the closest? This is 1D, so we can just calculate the distance between the first argument, the position at which we want to evaluate our model, and each training point. So let's say distances is the absolute value of position minus training XS. You may say, wait, what? Why does this work? Training is a position is a point, and training XS is an array. Welcome to NumPy broadcasting. So the idea is that when you say single value minus vector, then NumPy will interpret this that you mean for every entry in the vector, calculate single value minus that entry. And because that basically makes the expands position, which is a scalar, into a long vector, that's called broadcasting. It follows a fairly intuitive but sometimes complicated set of rules. So I will not explain broadcasting in much detail because that also generalizes to multidimensional arrays, and that takes some time to wrap your head around. But in practice, it's important to note that NumPy, if you do this, will implicitly assume that you want to do this for each individual entry of the vector. And that's very convenient because it means that we don't have to write a for loop in Python. Since whenever you do numerics, you should try to minimize the number of for loops that you actually write yourself. There's almost always a NumPy function to do the very same. So now we get all our distances, which is an array. So what we care about now is we want to know what's the closest distance, right? It's about the one nearest neighbor. And for that, there is a function in NumPy which is called arcmin. Let's take the following. I will just explain this a little bit. Let's say we have the values 2, 0, 3. Then arcmin returns 1, which means it returns the position at which the argument, so distances, is minimal. It doesn't return the minimum value, it returns the position where you find the minimum value. And you want this why? You want this because you don't actually care about what's the closest distance. What you care about is what's the corresponding label at that point. So you need some number to look it up. So we first use arcmin to figure out which entry in distances is the smallest, which tells us which data point is our nearest neighbor. And then we look up what's the corresponding value. Make sense? Okay, let's do that in code. So nearest neighbor index is just arcmin of distances. And now our single prediction is return training ys of nearest, where's autocomplete if you need it, nearest neighbor index. Is that understandable? Very good. Can we be more efficient? How many distances do we calculate right now? If I have n training points, how many distances do I calculate? N. If I query a lot, over and over and over again, do I need to calculate, say I query 100 times. How many distances do I need to calculate now? If I don't ask for one position, if I don't call this function once, but 100 times, how many distances do I need to calculate? One call is n distances, right? Between the one query and all training points. So 100 calls are, yes, 100 distance calculations. Which means if I'm going to query this function a lot, it's kind of useless to always calculate the full distances. You can be much more efficient. Any idea how you can be much more efficient? How what would you do? Sorting? Okay, sorting what? Yeah, yeah. So I sort that, and how does that help me?
Start both arrays and then just do the first to be the lower values for both.
No, so I query my function at different locations, right? And I have now my sorted XS, right? And I don't want to calculate 100 times n distances, because whenever you do that, this scales horribly with the data set, right? Make the data set twice as large, it's going to be twice as expensive to run the same prediction. Machine learning tells you that adding more data makes the model more accurate. That's brilliant, but if it's also more expensive, it's not exactly helpful. So how does sorting help me? The idea is good. Now, what do I do with it? Imagine you could rely on the fact that training XS and YS are sorted, so that XS is always increasing and YS is the right corresponding ordering. But XS is always increasing. Can you be smarter about it?
If the distances are getting larger, I know that I don't have to go other side. If the distances decrease,
Exactly. So what you could do is you can, for every query, if the training data is sorted, you can find the position where the nearest neighbor, where this particular position would be inserted. Imagine I have, again, my 3 training points here. That would be my data. It's sorted. And I query at this location. Which means if I know that this point in the sorted order would be inserted between that point and this point, I need to calculate exactly 2 distances. Namely, to the one neighbor and to the other, I have to figure out which one is closer. So if you have to query this thing several times, you will sort it once, and you can figure out where the one value has to be inserted by using binary search. Right? So you ask in the middle of the data point, so if that would all your training data sorted, you check what's in here. If that value is smaller than you query, you do the same on that half, otherwise you divide the other part. That way, you need to do a logarithm of the length of this in lookups and exactly 2 distance calculations, regardless on how big your training data is. Now, is scikit-learn going to do that for you? No. Sorry. So the libraries will not do all of this automatically, but it's important to think about that when you build large-scale predictions, there's a very intuitive, simple way to implement the individual models. But if you find yourself querying a lot of those, then it's really, really worth thinking about the cost of doing these predictions. And we see this regular in practice. If you build a model because it's faster, and then you apply it to 1 million systems, to 100 million systems, and then something which takes 0.2 seconds each is suddenly going to take a lot more of that. So it's important that you think about, at least when you actually use the machine learning models in practice, how to make that more efficient, right? So the straightforward query won't do the trick. This way you bring it from linear scaling in the training set size, you bring it to logarithmic scaling in the training set size, which is much more convenient for large settings. Is the rough idea clear? I won't ask you to implement this, it's a little bit annoying, but nonetheless, it's important to keep this in mind. All right, any questions on this code? It's fairly convenient for a machine learning model, right? So not overly complicated. All right, let's have a look at the predictions, shall we? So the task is to plot this together with the correct function, right? So we now know how to get our prediction, or we would like to see what it does. So I can build my training data. So I can say X as, or let's label this appropriately, train X as, train Y as is generate data set, let's take 10 points. And now we want to plot all of that, right? So we can do the scatter plot. Kind of looks like the function shape that we're looking for, right? If I do the same thing with many more things, then many more data points, it becomes more clear, right? But I want to emphasize what k-nearest neighbor is actually doing, so we do that in the limit of few data points. Let's stick to 10 for the time being. Now we want to plot also the true function. And to see that, I will build something which we call XS. It's basically our lin space again, 0.1 to 6. Let's take 100 points, so we see something. And then there would be, again, the Morse potential of XS. And now let me use plot, so we actually get a line, and we switch this around, so the line is in the background. So this is what we have, right? So we have the true function, and we can give this a label. So that would be ground truth. Now it's called a machine learning. The actual true value is the ground truth. And then this is our training data. So we do legend. Unhappy because I didn't do this right, not enough coffee. Right. So this is what we have. This is the actual true function, and we have our random training data points, which are these. So let's think about what k-nearest neighbors should predict. Probably get crucified if I start drawing on this, right? So What will be the prediction? What will the prediction be? Coming from the left, what's the nearest point? This one. So coming from here, the function value will always be the same until I reach this point. So my model completely misses the fact that the function keeps going. Now what's happening after this point? We need to think about the next one, right? So because we always take the value of the closest point, means until the middle of the true, we will predict that value. And then from the middle of the true, somewhere here, we will jump over there and then start predicting this value. So it's going to be a step. Let's visualize this because we have the code, right? So I have the XS values, and now I will get our corresponding prediction. PLT, what is that? Plot, we do. And it is XS, and it is predict nearest neighbor of each value X for X in XS. And let's say this label. This is the model prediction. That's not going to quite work because I need to give train XS and train YS. That should work. This is what we get. Everybody happy? Step functions, right? And between every 2 points, there's one step. Between every 2 points, there's one step in the middle. Because we're always taking the closest value. Anybody surprised by this plot? Or does it kind of match your intuition of what you think one nearest neighbor should do? So part of this is the reason why we do these things by hand is so you get an intuition. You start to get an intuition on how these methods work and when you can start to trust the model. Let's look at it. Does it reproduce all training data? Yes. Well, that's very good. We can at least expect that every model that we have reproduces the correct answer for our training data. That it does. Does it approximate the function? Kind of does, huh? Didn't ask about perfect. So what happens if I add more data? Does it get better if I add more data? Well, the steps get smaller, huh? So let's generate a larger data set. Take 100 points. Okay. Looks better, the approximation. More data points, more accurate. And we see the steps are smaller, right? There are some steps visible, but steps are smaller. If you look at this plot, would you say the model can be made accurate? Can you use that model? Maybe. Let me ask one question. Imagine you want to optimize a bond. You have two atoms, and you want to calculate what's the minimum bond distance. You know what the answer is, right? In our model, it's 1. Can you take a distance, say 2, and then calculate the gradient and optimize towards the minimum? Okay, let's make it a vote. Who says, yes, I can optimize following the gradient? Who says, no, you can't? Who doesn't want to answer? Okay. It's a tricky one let's take one step back. Let's take 10 data points again. Here's a new random selection of particularly helpful set of 10 data points. But can you really follow the gradient? Because the function is constant almost everywhere. So it has zero gradient almost everywhere. In fact, it has discontinuity. So you either have a singularity or you have zero gradient. So not exactly fun, is it? You can't go downhill. You can't optimize it. Sorry. But you could do some steps and see whether with more data points this becomes better. But you see that depending on what kind of random selection you have, maybe you don't even have a minimum, right? So if there's no data points over here, you miss that feature completely. Now, if you do nearest neighbors, many people have realized that those steps are not great, right? Those errors are huge. And yes, we can kill it with more data. That's true. But can you really do that in real applications that go beyond 1D? Because in higher dimensions, you need more and more data points to actually map out the function in sufficient detail. So at some point, you need too many of those. So one of the things that people came up with is K nearest neighbor, right? Where you take many points into account. And the way this is commonly done is not to take the average of 2 points, right? Because that does not strictly improve the prediction. Imagine we were to take the average for this particular case, right? What's going to happen? We have 1 point, we have another point. Right now, our model looks like this. We take the average of those 2 points, our model would look like this. Not entirely sure one is better than the other. So what people do is they use a weighted interpolation, where you say, if I'm closer to the left point, I should have a prediction that kind of takes this into account, that I'm closer to the left point. If I'm closer to the right point, I should kind of take this into account. So what you can do is you can do some weighting, or you can just do linear interpolation between the nearest neighbors, and that will give you a much better approximation because the steps go away. It also has one major advantage. You suddenly have a non-zero gradient, so you can optimize again. You will still have derivative discontinuities because this thing has a curvature, right? So if I take from this point to that point, it's exaggerate from that point to this point, the slopes are different, right? So it doesn't match exactly. But most optimizers don't care. As long as there's some way to go downhill, that's okay. And that's exactly what you would do. So in practice, you wouldn't use one nearest neighbors just because of the fact that you get steps, which can't be optimized and have large errors. But you'd rather use some kind of interpolant. You're free to do that. There's different ways. Linear interpolation is one thing. You can have something which is more weighted to try to match the derivatives, but by and large, that's the core idea. Is it clear where the steps come from and why this would be preferable? Now, I won't ask you to implement this yourself. It's not terribly difficult, but I want to show you scikit-learn. So are there any questions on what we did so far? Because otherwise I'll talk about scikit-learn. Okay. So far you had the luck that this particular algorithm is very easy to implement, right? I mean, it actually is a machine learning method. Most textbooks would be considered to be one, and it cost you 3 lines of very verbose Python. So that's not terribly complicated. The problem is that for many other machine learning methods, implementation is substantially more involved. And the other part is, you don't know beforehand which method is going to be most helpful. So you would like to have not only a way to try different methods, but you also would like to be able to try different methods without changing your code that you use time to write not to change it very much. And what scikit-learn does is it gives several machine learning algorithms, many in fact, the same interface. So all you have to do if you want to change from one algorithm to the other is to change the object that you instantiate. But you don't have to change the way how you build your data. You don't have to change how you plot your data. You don't have to change the shape of your data. Everything is the same. You just choose different algorithms for that by just changing the name. So the core focus of scikit-learn is not to give you the numerically most efficient implementation of a given algorithm. Right? Scikit-learn is not going to do the binary search for you. But what scikit-learn is meant for is save you time when you prototype a model, when you don't exactly know how to build this model, what it looks like, which algorithm it is, how you have to pre-process your data, how accurate it's going to be, what is the problem. This prototyping stage, that's where scikit-learn shines. If you later on say, I have my model and now I need to run a big calculation on the local cluster and it's too slow, I want to make it faster, then you probably have to find a more specialized way to do that. Scikit-learn is not known for being fast, but is known for being convenient. Even beyond scikit-learn, many machine learning libraries will use the same interface. They will behave like scikit-learn. They will look like scikit-learn because everybody knows it. So then it makes it easier to interchange with scikit-learn. So from that perspective, it's a very transferable skill. It does not depend on your actual problem at hand that you have, but it's rather just a list of algorithms. I will explain the core idea of that, and we will use it to check out our two nearest neighbors, to play around with it, so we don't have to implement it yourselves. All right. So let's try scikit-learn. I kind of relied on the internet to be fast, which all right. If you check the webpage, I will walk you through how to build a certain model using scikit-learn. Scikit-learn is a huge library, just like NumPy or Pandas or Matplotlib. I'm probably using Python for almost all my work for maybe 5 years plus now, and I'm still discovering new functions, right? So this is a huge library. You see this sorted by the method category, whether you want to do classification, maybe regression, clustering, or whatever you care about. Let's look at the regression section, and you will see there is nearest neighbors, because it's a very common regression problem. So if you go there, it will give you some kind of high-level introduction what the algorithm does. And the documentation usually gives you some visual interpretation. Here you see the same steps that we just programmed ourselves, but you see the same visualization, which exactly tells you what the k-nearest neighbors is doing. In this case, it's 5. And here you see this is k-nearest neighbors, where you take 5 neighbors, but you weigh by distance. And you see that the function is approximating the data points very closely. You can also do this with faces. This is really nightmare fuel if you want to look at those. But it also will explain, will give example code usually. Let me check. Yeah. So I will quickly walk you through what it does. You import from the library sklearn, you import the neighbors section, submodule. And then in scikit-learn, the logic is always the same. You build an instance of a model. Instance is a Python object. So you say from neighbors, please give me a k-neighbors regressor. You need to tell it, so it tells you what it is, right? K-neighbors. And also tells you the problem that you want to solve is a regression problem. And it's important that you choose the right one, right? So there's also a k-neighbors classifier. Well, we don't want to classify, we're going to do regression. So you do k-neighbors regression. Now, once you have this object, here you can give the corresponding parameters, right? You say the number of neighbors that you want, 1, 2, 5, 50. And you can specify more options that we will discuss in just a second. And it works the same way for every algorithm. It doesn't matter whether you want to do k-nearest neighbors, if you want to do decision trees, if you want to do kernel methods, if you want to build your neural network, the logic is always the same. It's, you have this object that knows about the parameters of the method, but currently it doesn't know about the data. That's what happens in the next step. You have this object here, and you call object.fit, which trains the model. This is the training step of the model. And it's always called fit no matter which algorithm you choose. The way you call it is the same. If you want to go to a decision tree, then what you change is this, right? To the decision tree regression. That's it. Everything else remains the same. The rest of the code is exactly the same. That's the purpose of the library, that you can easily exchange this to just prototype what's going on. Fitting always takes two things. Capital X, that's a convention in scikit-learn that your feature matrix is called capital X. Remember, features are the positions, right, where we evaluate our individual function. So of our training data, that would be x1, x2, and so on until xn. That is capital X. And then you have y, which are the corresponding values. And that is lowercase y. Now, who can tell me why this is a capital X and this is a lowercase y? In mathematical notation, when do you use a lowercase and when do you use an uppercase? Yes. The matrix gets an uppercase and a vector gets a lowercase. Why would X be a matrix? Because not every problem that you learn is one-dimensional. In our particular case, it's one-dimensional, it's just a value. But it could be a two-dimensional thing, and then every entry would have one component, the X component, another component, the Y component, right? Would have two features. And this can be many, this can be 20. That's why every row is what belongs together, right? The row of the X matrix is all features, and you have one scalar value label for this. And that's why y always will be a vector, because for every training point you have exactly one label. Is that clear? That's going to trip you, because if you now try to do this with scikit-learn, your 1D problem, keep in mind X needs to be a matrix, not an array. Scikit-learn will complain about the fact that if you just make this a vector, that it has the wrong shape. So make sure there's actually a matrix of one column. Is that clear? All right, so let's go back to our logic. So you do fit to train the model. You give all the training points that we have, you give the corresponding labels that you have, and then you can predict it somewhere. So dot fit gives you the trained model. Afterwards, you can do dot predict to infer new values. That's what we call the fit predict API or signatures. That's a very standard thing. So to go back, I will write some pseudocode to give this in. You would typically write CLS for class. This is model, so some model regressor. Then you do CLS.fit of XY, and then you can do CLS.predict. Any scikit-learn code that you will write basically looks like this. So you choose some kind of regression algorithm. You tell it to fit your vector, your representation vectors to yield corresponding labels. And then you can query the model to give approximated labels for the new set of query locations. Is that clear so far?
Does this X prime value is not contained in the original value, right?
No. Yeah, so basically in the logic would be X is training data feature matrix, right? Y is training data labels. And then inference is X prime is query feature matrix, and then Y prime is the label for this feature matrix. They can be different, right? So of course you can ask your machine learning model to give you the answer of what it thinks the value is where it had the training data. And in fact, some models will give a different answer from the actual labels. We will see this tomorrow. But in principle, you would make them disjoint. Is that logic clear? Very good. So then I will leave this open so you have a rough idea. And I will leave this for orientation. I know the code doesn't work. Not supposed to. I would ask you, do number 5, which is basically do the same thing as number 4, but this time using scikit-learn. Please do the one nearest neighbor first, so you get the same result as before. You can compare it, and then we will move on to the 2 nearest neighbors. Yeah.
I was able to do the plotting. When I was going to make the graph, the number is wrong. But I have here that I have the predict function. But then when I plot it, not supposed to be there. Yeah, this one I can of course. So this one that uses this function. So yeah, this is not the same thing. This is fine. How do I plot the actual data versus The last part here is to plug everything together. So that, like this one. That. This one. Which is to do this operation here for
Keep in mind that this code is not supposed to work, right? This illustrates the structure. This regressor needs to be something particular, X, Y to be something particular, right? All those structures. If you don't feel quite accustomed to scikit-learn yet, that's okay. We're going to have the full day tomorrow to use scikit-learn a little more. Because tomorrow we will first implement something again by hand, in this case called ridge regression, and then we will pawn this off to scikit-learn so you can play around with it and see what the difference is between the two methods. But for the time being, let's get slowly used to what scikit-learn does. So the first thing is we would need to know what kind of regressor we care about. Right, so called some model regressor, we want something else, and of course that's the k neighbors regressor. You can look this up in the documentation. There you can look up the different algorithms. It will tell you which corresponding regressor you want, how they are called. So in this case, it's sklearn neighbors k neighbors regressor. So we will copy exactly this. And we have our k neighbors regressor. All right, now what is the training data feature matrix? Look at our previous code, so we do exactly the same thing. Let me copy this. Make this a little smaller so it actually fits. Okay, so this code is exactly as before, right? Build us some data set, and you understood what this is doing. So that is the generated data set. That is the x-axis position. This is the truth answer. So now what we do is we build our regressor. And now we need just to give it an x matrix, right? The feature matrix. Now is this thing here. And that is supposed to be a 2D thing. So if I did not take this into account and just put train xs here and say this is train ys, I leave the variables so you see the direct connection to the other code, then this is going to fail horribly. I'm going to tell you that 2D ain't 1D. It says, sorry, I expected a 2D array, but I got a 1D array instead. That's the difference between X being a vector or a matrix of one column. So let's change that. So that should give us unhappy. Why is it unhappy? Yes. 110. Then let's do this. I will explain what it does in just a second. Let's say we have a 1D array. 1 to 3 is a 1D vector. Now, I can use the colon, which is the indexing in NumPy arrays or in Python in general. And this means it's the same thing, because I take the full array. I use the index, but I say from start to finish. Now what you can do, in NumPy, you can index several dimensions. Right? You can, if you have a two-dimensional object, you can index every dimension separately. And you separate them by a comma. You can only do this in NumPy. In regular nested lists, this doesn't work. Now what you're seeing is this adds a new dimension. So you get You now see it used to be like here, one set of brackets and the one vector in between. And using this, you get the new axis, how it's called in NumPy. The separate dimension is called an axis. And that's how you get the corresponding separate entry. If you don't like the none, because it's not very intuitive, you can also use NumPy new axis, which is exactly the same thing, but explains a little better what you want to do. Right? So NP new axis means make this a 2D thing, please. If you want to know more about it, that is called advanced indexing. It's also part of the course, which explains this in a little detail with some examples how this works. So if you don't know it, it might be worth looking it up. All right. So let me use the same new axis so it's easier to understand. And up until the fitting, it's fine. Right? So now we have the inference, right? We're gonna want to get some predictions here. After all, that's a model. Huh? So what's x prime? X prime is again the feature matrix of the points that we care about. So again, we have to take whatever points we have, the 1D array of points, and convert this into some 2D thing. So you will probably not be terribly surprised that the answer is this. All right, it's the same thing just as before. We add another dimension. The same way we did this for the training data, we now do this for the variable that contains all our prediction points. Everybody happy? Okay. So let's predict. Okay. Not complaining. So now we can start plotting. And because I'm lazy, I will copy and paste. So now the difference is that here we use y prime. And the rest should work. Is that doing what we want? Yes. We didn't specify how many neighbors we want. And what it did is it used the default value, which is 5. That makes sense for a lot of people, but right now, not for us. So let's do this again, and now it looks like we think it should look, right? This is the one nearest neighbor prediction. This time with scikit-learn. Everything clear up until here? Very good. Okay, now one of the nice things about having computer code is the fact that we can just play around with this arbitrarily. We can change stuff. And that's how we build intuition. That's how you learn. So let's go change some stuff. Let's change k. Right, we just did it. So let's change it to something else. Let's change it to 2. I feel like 2. Okay, what do we get? Does it make sense? It's always a good idea to question whether what you think the code does is what the code actually does. So if we take the 2 nearest neighbors, right, that would be, for example, this point or that point, we're very far away from each other. So we say, okay, it takes the average of the 2, so it takes this one weighted first, and then it takes that one. That's okay, because as of here, that point is actually closer. So it takes the average of these 2 points, which is that value. But up until the middle of these 2 points, those 2 points are the closest, meaning it predicts the average of the 2. Sounds reasonable, right? Now, if you look at this, the one nearest neighbor would have a high barrier, right? The one nearest neighbor would actually have this high repulsive wall over here. 2 nearest neighbors, not as high anymore. Let's make k bigger. Who remembers my slides? What happens when you make K larger? Yeah. Yeah, you lose resolution. Let's say 20. No, can't do that. You only have 10 data points. Let's say 10. Who knows what the plot is going to look like? Do we have a minimum? Why is it a flat line? Because I always predict the average value of my 10 nearest neighbors, and I happen to have exactly 10 data points. So not so great. Which tells you that you have to find a way to figure out which K is the best. And this is usually done by building models repeatedly and seeing what's the average accuracy thereof. This has to be done using a certain procedure to make sure your model is actually reliable. We will not have the time probably to do that, to learn how to do cross-validation properly. This takes actually more of a real lecture. But we will do some sketch thereof tomorrow. Okay, so let's use more data, right? Because the problem with the 10 nearest neighbors is the fact that we only have 10 training points. Let's take 100. That looks okay. Huh? Now, let's take more data points. 1,000. Curve looks smooth and smoother, right? And in fact, you can show, and this is a formal guarantee. There's a few things that mathematicians will give guarantees about in learning, but if I have the logarithm of the number of data points in my training, and this is the logarithm of the mean absolute error, then in the limit of very many data points and subject to some conditions, what I can expect is a straight line. In other words, to be more accurate in modeling an arbitrary function, I need exponentially more data. So my function value, as I have 10 data points, my approximation is very bad. With 100, I get more accurate. With 1,000, I get even more accurate. But the rate at which I get more accurate is this. There's a long list of conditions when this is true, but in practice, it turns out that fulfilling those conditions is easy. So you can expect if you make this plot, it's called a learning curve. To make those plots in building a model, it tells you whether the model you have is actually able to make use of more data, right? Does it get better as you add more data, or is maybe your model optimized, that it's not flexible enough to actually incorporate additional information? That could be. To give you a simple example, imagine I fit a single linear function. What's going to happen if I fit a linear function? It's a bad fit, right? It's going to be something like the plot that we've just seen. Is it going to improve with more data? No, I mean, once you have enough data, is not the problem that you don't have enough data to describe the function. The function is not flexible enough. Exactly, the most potential is not linear. So what's going to happen is that your learning curve is first very steeply increase, and then going to be a flat line, because adding more data doesn't help. So this learning curve is a diagnostic tool that tells you, can I actually make good on the promise of machine learning that adding more data is good? If it doesn't pay off, then something is wrong, and it's usually your model or the data. But One of the two. All right. Let's take one step back and answer some questions. So I still have a handful of minutes. I will use that to discuss with you the questions. So we won't do number 7. We will just talk about the plot that we have right now. So we're supposed to play with a number of training data points and the parameter of the k-nearest neighbors. And in doing that, we should focus on a few number of data points. What do we observe? Well, we saw the steps, and we saw that if we have very few data points, we can't have very large nearest neighbors. So how can we choose which parameter is best? So which, for example, the k-nearest neighbors, which k is the best? It should be the k that has the minimum error over the whole domain if you draw random training data, right? So the way you would do this in practice is to generate random training data. You would build the model, you would calculate what is the mean absolute error over my whole function. Then you would choose the k that for a given number of training points is accurate. If you think about it, that's starting to look like a lot of nested for loops, right? So for a handful of random data sets, calculate the fit model and predict all possible values over the range, another for loop, and then figure out what's the optional value. And that's in fact what you have to do, because with a machine learning model, there's a difference between the training error, so how accurate you are on that data, and the testing error. So basically, what kind of accuracy can you expect on unseen data? And to model that one, you need to do the cross-validation accordingly. So how does the fit quality improve with more data? We could now make this learning curve plot numerically, maybe tomorrow, by just calculating the mean absolute error. But I would like to focus on the question on which region is hard to predict and why. Just look at this function. Any idea which part of this is hard to learn? Right? Near the minimum. This one you say is hard to learn. Okay. Why?
The start seems like a line and the end as well.
I mean, this is more linear, and then that is rather linear, and then in between you have the high curvature. So in high dimensions, that's exactly true. Regions of high curvature are hard to learn. Let's visualize this. Let's go back to something meaningful. 10, yes. 10 and 2 nearest neighbors. I think this plot probably illustrates the answer quite nicely. So with this particular thing, you have the problem that if you have a high gradient, then your 1 nearest neighbor struggles and your 2 nearest neighbor struggles as well, right? So it's hard to describe a region where you have a steep descent. And there's another problem. It's hard to describe a feature at the border. Look at the right side of our training data. The model is reasonably accurate. But why is it reasonably accurate? Because our potential already is almost constant for large values, right? If I make this plot to continue to 100, remember, this was a flat line. So any model that has any data point after this is going to be perfect to infinity in that direction. On this end, it doesn't have a data point, right? The largest data point I have right here is almost the minimum, which means I don't see this part, right? It's a big feature at the border of my domain. Unless I have a lot of data points, I will not see it. And that's exactly the problem. Machine learning methods rely on interpolation. Right? I have a bunch of points, and between those points, between my left point and my rightmost point, I have something which is an approximation, which I can assume to work. But in either of the two sides, all bets are off. This is not interpolation anymore, it's extrapolation. On one side, we just get lucky. But on the other side, we see the problem. Is that clear? Now, you will be frustrated to hear that in high dimensions, almost every point is outside your training data. So when you read in research articles, machine learning is interpolating in high dimensions, well, it's not. But you can also show that the predictive power of that still is good. But in low dimensions, you really see the problem. So that means that regions which are hard to learn for this particular problems are exactly the boundaries of your data set. And we'll see this tomorrow, that even with more advanced methods than k-nearest neighbors, this effect is present. All right. Now, for higher dimensions, what does it mean? We will need many, many more data points. Right? So with the 10 points, we probably can't do it. And the other part is, in higher dimensions, k-nearest neighbor is not exactly fun, right? Because you can't easily interpolate in high dimensions between the nearest neighbors and expect this to be a smooth function. That's why you would use a more advanced method of that, which is kernel-based methods, and we do that numerically tomorrow. About everything today, I know it was a lot. Do you have any questions left? Yeah.
When you define the data type for the array, and you call the cyclic word, you said that you should use unified data types. You can see that.
NumPy D types. So you can, when you call scikit-learn, you should use NumPy arrays. Scikit-learn internally will use NumPy for that. And it will probably almost always cast towards the right data type. So scikit-learn should not complain.
You can see that on your
So we have XS to be this linear space, and then here we add the new axis.
that automatically creates a NumPy array.
This already is a NumPy array, and this extends the NumPy array by one more dimension. All right, now what would help me for the next days is if you can give me a brief show of hands on whether the difficulty level matches your experience, so whether it's too easy or too hard. So usually would expect for roughly 1/3 saying, okay, 1/3 too easy, 1/3 too hard. So the question is, how do you feel? So who says this is too easy? Who says this is too hard? So everybody else is just happy or too tired? Okay, if it's kind of okay, that's okay. So then we will try to do the remaining days on roughly the same difficulty level, so that this works for you. All right, then thank you very much for the 4 hours. Very good, and see you tomorrow.